Hi, and welcome to the Danfoss, I guess we'll call it the Danfoss video line on HVAC and our topics. This is brand new for us, so we kind of don't even really have a name for it yet, but this is something we thought we'd do as a pilot project and talk about various topics that we've been getting questions on in the past. So I do a lot of training. I train a lot of contractors. I train a lot of wholesalers. And do guest lectures at schools, and generally people come to me, and they ask me a lot of the same questions over and over again. And we thought, let's put together some kind of video series where we can cover these questions that we get, and people can respond to the videos, and they can ask more questions, and we can kind of go through and do a series where we're answering all the questions that you have but may not get a chance to ask somebody. And this is going to be, viewer driven. We've already selected a few of the first number of topics we're going to do, but going down the road, we're going to be basing our video series more and more on what you guys write in and ask us to cover. Now, my background, I've been with Danfoss for about 20 years, and I'm an engineer, and engineering technologist, as we call it here in Canada. And one of my first jobs, really, that I can think back of was working what's called the warranty pile. Now, nobody liked working the warranty pile, but the good thing about it was you kind of got a chance to see why everything fails in the field. So I saw all kinds of burnouts and floodbacks and everything else. And to be honest with you, it's pretty true. 1/3 no fault found, 1/3 baked, and 1/3 drowned is kind of there's a lot of truth to that, okay, as far as what we got back, anyways. And on top of that, then I was a field service engineer for a while and went out to a lot of job sites and found out why things were failing or they weren't operating the way they were. And again, if you were to take all of these situations, there was a few quirky ones, but most of them came down to charge, airflow, and to a lesser extent, some of the electronic controls weren't working as they were supposed to, or they weren't integrated properly. But again, they were a vast minority. The big issues we had were when compressors started dying and or people were complaining that, the refrigeration system wasn't working the way it was supposed to. You go out there, there's always a good reason for it. Okay. And that reason 90% of the time was application related. So what we're going to talk about today, and we're going to focus on compressors, by the way, is how can you do a quick inspection, preventive maintenance, or if you are replacing a compressor and you're doing a startup or commissioning, how can you eliminate, 90% of the reasons why that failed in the first place? Replacing something and not knowing why it failed is, probably the ultimate version of gambling. Okay. If you haven't eliminated that issue, chances are it's going to fail again. And, we've seen this in the field where you get your third compressor back from the same installation and suddenly everybody connects the dots, digs their heels in, and finally figures out, we got to figure out what's wrong here. Okay. So dealing with the compressor, keep in mind that the compressor itself is one part of a system. So you look at it, it doesn't look like much. What does the compressor do? Well, it takes a low pressure vapor or pumps it to a high pressure vapor. Okay. That's kind of its job. And when it does this, it uses energy in the form of electrical, okay, in its motor, and it generates heat. So the compressor is doing work, it's generating heat within itself, and it's relying on the refrigerant gas coming back, as well as some surface heat removal, but mostly the gas coming back on the suction side to remove that heat, okay? And then, of course, that motor heat, or the heat of compression, combined with your evaporator heat load, is then sent out and rejected or gotten rid of in the condenser. So as long as that compressor operates, pumping a dry vapor, okay, and it operates within the correct temperature, it's going to last just about forever. Okay, they have this very, this area where they like to operate called the application envelope. And as long as they operate within that, they're happy. Okay, so if you see a compressor that's been operating for 20 years, there's a good chance it's never really seen bad voltage. It's never had excessive superheat or suffered a loss of charge. It's never had a really, really dirty condenser, okay, or a bad start or run capacitor, or any of these things. Okay, all of these things aren't the compressor. but they affect how that compressor operates and how happy it's going to be. Okay, so if you want to use the term keeping your compressor happy, there's where we need to focus on. So let's start with some of the things you want to check. All right, obviously, the compressor inspection, check the terminal box, make sure there's no dings. That terminal box should be on there tight. Okay, it's keeping dirt and debris out, which you don't want in around the electrical contacts. Check your electrical contacts for discoloration. All right, there should be no corrosion. They shouldn't be black. The conductors themselves or the spade connectors or whatever they are should not be discolored. They shouldn't be burnt, or the metal shouldn't be blued from overheating. If this is an issue, there is probably a case of either a poor connection or the previous compressor, if you are replacing one, probably locked up and drew locked rotor amps, or had a faulty start cap and was hesitating on startup. It didn't have enough starting torque to overcome the pressure differential, especially if you use a TXV, which doesn't allow the system to equalize in the off cycle. Doing that, the compressor is going to pull about 5 or 6 times its normal current level. Okay, and this is going to cause rapid heating up of the components. So a visual inspection, don't ignore the electrical side. Okay, it only takes a second to do a quick look. If anything looks out of the ordinary, find out why. Okay. The next thing is take a look at the start hardware. Okay, the start cap, and if it's there, if it's a high starting torque compressor, look at the run cap. Check their values, even during a preventive maintenance session. Okay, check them. It only takes a second. All right. Does the compressor start relay pull in quickly? Is it buzzing? Again, is there discoloration? Does it look like there's been any issues? Do you see heavy pitting or anything on the contacts? All right. This is cheap insurance to ensure that the compressor, which somebody invested in, is going to continue to operate. Okay. If your system is starting up, again, make sure that compressor starts right away. There shouldn't be any hesitation. If it even hesitates for a couple of seconds or even a second before it fires up, keep in mind those windings are going to get very, very hot. There should be no hesitation whatsoever. If there is, now you got to find out why. My recommendation would be, obviously, check the voltage. Okay, it's one thing to check the voltage when the compressor is not running, but it's kind of like a car battery. You can read 12 volts at a car battery, but as soon as you put a load on it, boom, the voltage drops because you've got faulty plates inside. Same goes with a power supply, AC power supply. You put it under load. All right, when that compressor starts up and is running, check your voltage. Okay, and remember, in the application guide for a compressor, you'll get a voltage range, and it's pretty big. All right, what a lot of people don't realize is that's only for momentary purposes. Okay, that's not to say the compressor can run at 196 volts when it's supposed to be 230 or whatever. Yeah, if it operates at 196 volts for 30 seconds or a minute, that's fine. But if it runs continuously at that, that's going to be a problem. Your current's going to be a lot higher, and your motor life is going to drop drastically. As an aside, I checked with a motor manufacturer, and he gave me a quick formula to determine current and motor temperature. And when you plug the numbers in, it was amazing how rapidly the life expectancy of that motor, i.e. the motor insulation, line insulation, dropped with an increase in current and an increase in temperature. It was quite dramatic. So this is definitely something that you don't want to ignore. Obviously, I understand if it's an issue of poor power factor or something that we can't cover today. Maybe we'll cover it down the road in a future video. You're not responsible for that. But, the owner has to know that if you've got really crappy voltage at your compressor, yeah, you can change that compressor. But, you're going to be doing this again in the near future. All right, it needs to be corrected. Again, that's not up to you, but the owner has to be notified of that, because unfortunately, it's, you're throwing good money after bad in that scenario. All right, unless you eliminate the original cause of the failure, it's going to happen again. So check your voltages and current. Well, a lot of people don't realize, and I mentioned it already, is, I'll get a phone call and say, Jamie, I've checked my, condensing temperatures and pressures. I've checked my evaporator pressures and temperatures, and my current is, 15% higher than it's supposed to be. My voltage checks out okay. It kind of stumped me at first. And then I had to think back. I'm like, can you check power factor? Do you have a power factor meter? Because if your power factor is 0.8, right, instead of 0.98, that compressor is going to draw 15 or 20% more current to give you the same capacity. All right. Well, you're not pumping any more refrigerant with that extra current draw, which means your motor temperature is going to be that much higher. Okay. So once again, check your power factor. This is something that's not as uncommon as you might think, especially in remote areas like, say, golf resorts and things like that have a long run away from the main lines. All right, you can end up getting some crazy or wonky voltages. Marinas, anything like that can have real issues. Okay, so again, don't ignore it. Do a little bit of study on this. You'd be surprised how many times that would have been a solution. All right. The next thing you want to look at, if everything checks out in the compressor, you've checked your voltages, your current draw, if that checks out fine, great. You've eliminated a big issue of failures. The next thing you want to do, of course, is, and we might as well start with it now, is charging. Okay. When you charge a system, and I shouldn't even have to talk about this, and I know a lot of people are probably going to roll their eyes, and that would be great, except for one thing. According to some stats I looked at, more than half the units that are out there, or almost half the units that are out there, are overcharged. And when you consider the push for efficiency and everything else these days, people are paying for CR18 systems. You're not going to get CR18 out of that if the system isn't charged properly. It's a huge issue. All right. So go by the manufacturer's specs. Get yourself some good thermistors or whatever you need on your meters. Measure and charge. If it's a TXV system, charge according to subcooling. Okay, you can measure your indoor and outdoor pressures. You know what your wet bulb's going to be inside. Okay, measure all these things and charge it correctly. It's not going to take you a ton more time. All right, and if it's done correctly, at least again, you've eliminated a major issue with systems failing. Okay, if a system is overcharged, and I mean substantially overcharged, where's that refrigerant got to go? Right? There's only so much volume inside of a system for the refrigerant. So in the off cycle, there's a much greater chance it's going to make its way back out to the compressor again. And when that compressor starts and the sump pressure drops, that oil is going to foam. You're going to lose lubrication. Okay? And don't kid yourself. People think scrolls are liquid proof. Yeah, a scroll will take a liquid slug. That's great. But that lasts seconds. All right? They still got bearings. They still need to be lubricated, especially that upper bearing right below the scroll. So if you end up having a situation where you've got liquid return, poor superheat or poor metering control, you've got off-cycle migration, right? That upper bearing is going to fail. I don't care what kind of compressor it is. In fact, scrolls in many ways are more prone to failure because of that than other types of compressors. So don't be fooled into thinking that a scroll compressor is this bulletproof thing. All right, trust me, I know. I got a pile in my warranty pile that died because of basically liquid flood back or whatever that washed that bearing of lubrication and it seized up. And man, you want to see a mess. You look inside of a compressor when that bearing seizes. You got that counterweight swinging around there. It ain't going to stop. And it just keeps going and shreds everything up inside of there. The scrolls lock up, the Oldham coupling smashes, and everything is a big pile of rubble inside. And sure enough, that bearing's tight as a nut. Okay, so keep that in mind. All right. Of course, when you're charging, another thing you got to keep in mind on is airflow. Airflow is a huge issue again. Okay. And it's kind of a tougher topic because a lot of times, you're at a house, you're at an install, the ductwork's already there, it's buried in the wall, and you go and you measure CFM. It's supposed to be 400 and you've got, 286 or something like that. Right. Well, there isn't much you can do as far as the ductwork side is concerned, except make a recommendation. Okay, like we talked about power factor already. Fixing ductwork that hasn't been installed correctly is not a cheap thing. All right, it's a huge part of the install cost. So, that's not maybe an easy topic to broach with a customer. But the flip side is, and I'll say this again, if the guy's paying for a CR18 system and his airflow is to the point where it's seriously compromising the system, he's not going to get CR18. He might have a CR11 system if he's lucky. Okay, so again, that's a decision that has to be made, how to correct that airflow. Now, if it's just a matter of a dirty coil, if the coil looks like a cashmere sweater, or if there's, stuff in the ductwork that's blocking airflow, or whatever it happens to be, if it's something fixable, obviously catch it and fix it. Okay, because if your airflow is not correct, it's pretty hard to know what is actually wrong with the system, as we've talked about before, and a lot of people have talked about this. So verify airflow. If you're not sure how to do it, we'll probably be talking about that in a video down the road. But again, there's lots of online materials that will teach you how to do that quickly and effectively. Okay, it's not as hard as a lot of people think it is. Okay, so again, we're not talking about a compressor here, right? But the compressor, unfortunately, is the one left holding the ball when the rest of the system isn't doing what it's supposed to do. Okay, and it takes the fall for it. All right, it doesn't matter if it's a plugged TX valve, a failed fan motor, recirculating the air in the condenser. All these things add up, or end up in the same possible way, with a dead compressor or a system that's, not going to live nearly as long as it's supposed to live. So don't ignore the rest of that system. Okay, so checking airflow, look at the condenser outside or inside if it's inside. Is it clean? Is it being blocked? Is there a fence around it? Is there a hedge around it? You'd be surprised the stuff we've cleaned away from outdoor units. I've got pictures of tree, bush stumps and stuff like that around an outdoor unit where there used to be a hedge or a tree growing. Finding snakes and lizards and everything else living in these things that, wrapped around the compressor relay. And, the system is dirty. And when we clean all that stuff up and clean the condenser, we operate at about a 15 or 20 degree lower condensing temperature than we were before. So think about that, right? Again, you got a high SEER unit, you run your condensing temperature 20 degrees higher than it's supposed to be, you're not getting no high SEER system. Okay, you're getting a low SEER system that you paid a high SEER price for. So once again, how do you broach that with a customer? A lot of times being a good tech isn't necessarily being technical. It's how do you convey your ideas to people so they can agree with you. All right. People don't want to have that outdoor unit being looked at or being seen. So they do all kinds of stuff to cover it up. But they have to also be aware that there is a cost to that. Okay. And it goes beyond the $20 a month in extra electricity. I mean, you can be talking about, reducing the life expectancy of that unit by 5 or 7 years, right? The replacement cost should be a real concern there. So, don't let this go. Don't be afraid to talk to people about that, okay? And I'm talking about easy cases. A lot of times, air being recirculated in a condenser is a real issue. Condensers are stupid. They don't know what the actual outdoor ambient temperature is. All they know is what is the temperature of the air that's entering into them. So they don't care if it's 85 degrees outside. If it's recirculating the air and if the air going in is at 100 degrees, okay, they think it's 100-degree ambient outside, and that's the way they're going to operate. Okay, so again, keep in mind that this is an issue that needs to be addressed, even though we're just talking about compressors. We're talking about startup commissioning or, preventative maintenance. Okay, that should all be on your list when you're out there. All right. So we talked about, the electrical side, the refrigerant side, suction and discharge. We've talked about charging and airflow. Let's kind of move forward. We'll kind of wrap this up in a little bit. I just want to talk about a general inspection again, is the mounting of the compressors. Now, you may not think much about this, but, I've been to jobs where you get up on the roof of a building and there's a pool of oil on a tar roof. Now, oil and tar roofs don't mix very well together, and you can end up in lawsuits and all kinds of other issues. What ended up happening was this was a tandem application, 2 compressors operating in tandem, which means they share the same suction and discharge headers or connections. They're designed to operate. They're not, let's put it this way, they're not allowed to move independently of each other. Okay, they have to be fastened securely to a common rail. They should not vibrate or be able to move independently of each other. There may even be a bracket, a securing bracket that goes across their heads that attaches them to each other. They cannot move independently because they share a common suction and discharge. If they move independently, you're going to crack, damage, destroy all those connections, including possibly your suction or your pressure control connections as well. So again, when this happens, it can be a real issue. All right, it's not just a loss of charge, right? It can get a lot deeper than that. So they're designed to be mounted rigidly to a bar, and then that is sprung or isolated from the rest of the building. Okay, so the tandem rail they sit on is designed to be isolated itself on the bottom, but unless specified specifically otherwise by the manufacturer, those compressors need to be mounted to that rail, okay, firmly, okay, rigidly, so they don't operate independent of each other. Moving away from that, even something as simple as a basic compressor. All right, if you look at the installation guide, there is a torquing requirement for those grommets. Okay, a lot of times they come from the manufacturer torqued right down, so they're rigid. That's not the way they're supposed to be, living their life when they're operating. That is just for transportation, so they don't, bang back and forth in the unit during transportation. Loosen them off, torque them to the way they're supposed to be, so it limits vibration, it limits noise, it reduces the component shake inside the motor and everything else inside of the compressor. Don't forget that inside the compressor shell, there could be connections, pipe connections that connect to the actual compressor guts itself. So if it's allowed to move inside of that compressor in a way it's not supposed to, you're going to drastically reduce life expectancy of those connections. Okay, and you can actually have a breakage inside the compressor itself. Okay, so again, make sure if the grommets are all chipped or they're missing, one of them isn't there, check that and make sure the compressor is secured properly. Okay, we've already talked about the terminal block, the electrical box cover and things like that. All right, I'm going to tell you one more time. Okay, make sure you secure that the way it's supposed to be secured. Please don't leave that off as a convenience to the next guy. Okay, make sure that everything checks out there. Okay, if anything gets inside of there and shorts it out or causes a problem, it's going to be an issue down the road. Okay, so again, just to recap, we've kind of covered a lot of different areas. You thought, well, this guy's supposed to talk about compressors. He's talked about everything else other than the compressor. Well, that's true. Because again, the compressor is, unfortunately, the one left holding the ball or the bag, what you want to call it, when something else in the system fails. Okay, so doing a quick walk around, making sure everything in the system is operating correctly, do all your checks, electrical, do all your checks on pressures and temperatures, your airflow checks, right? I'm not going to turn this into a piping video, but again, if you see places in the piping that are going to trap oil, right, or if you're not sure about piping design that can trap oil, again, there are things that you can go online and learn about. I will say this though, if you got a split system, okay, where the compressor or the condenser or the evaporator is above the compressor, the piping off of that coil should rise above the top circuit in that coil. Okay, this will stop refrigerant from draining out of that coil back down into the compressor. That's a big one. I've seen a few jobs where that wasn't done, and you can guess the results. Oh, but I had a crankcase heater on the compressor. The crankcase heater isn't going to boil off gallons of refrigerant in a short period of time. It's only 75 or 100 watts. Okay, it is designed for one thing, and that is to keep the oil temperature warmer than the saturation temperature of the system by about 10 or 15 degrees. All right, and this drives out any refrigerant or stops migration of any refrigerant from going to the oil. All right, it's not going to happen. It is not designed to boil refrigerant off out of the oil that's draining back there at a rapid rate, no more than it's designed to replace a suction line accumulator, okay, that's going to trap liquid coming back. So again, from piping's perspective, that's one you want to look for. All right, so again, we're kind of wrapping this up. I'm sorry if I kind of jumped around. This is our first kick at the can, but going forward, please leave your responses to this video. Please give us questions on things you want us to cover, things we can do differently. Going forward, again, I'm going to have some samples I can hold in my hand when we're talking about components and things like that, but this is just a trial run to see how we're going to do this. Okay, so anyways, I hope to talk to you in the future. Thank you for joining us. Be safe out there, and hope we'll talk to you soon. Take care, guys. Bye.